about finding zeros of polynomial functions, and we've already been doing this. In 2.4, there were those problems 40 and 44 and 48 where we finished solving the equation. That's all you're going to do here. This is not really anything new. The only thing that's new here is that we get a couple of theorems that help us determine possible zeros, because they're not going to give you the first zero in this section. In 2.4, they gave you the first one, right? And then from there, you plug that into synthetic division and you found the rest of them. Well, they're not going to give you any zeros. So you've got to find the first one by yourself. So first of all, please look at page 327 in the study tip. And remember of all the different kinds of zeros that you're possibly going to be getting, right? It could be square roots. It could be things that have I in them, so it could be complex number solutions. And, of course, then you have just the regular rational number solutions that are nice. So don't forget that you have all of those possibilities for solutions. The first theorem is the rational zero theorem. That's section 1. The rational zero theorem just tells me all the possible rational numbers. This does not give me any insight into any possible complex numbers or irrational numbers. It just gives me the possible rational things, the ones that are nice and easy to use in synthetic division. So the first thing I got to do is I got to remind you of the notation. When we use the polynomial notation, remember we talked about it's f of x is equal to a sub n, x to the n, plus a sub n minus 1 to the x to the n minus 1, all the way down to a sub 1, x to the first power, plus a sub 0, right? Where the a's are just the coefficients, n just being the highest exponent that's there, and we put it in descending order, all the way down to the constant term. So the rational zero theorem says that if there is a rational zero for this polynomial, then it has to be of the form a factor of a sub 0 divided by a factor of a sub n, which most of the time I rewrite that in words for folks. It's a factor of the constant term divided by the factors of the leading coefficient. Okay? Okay, and they give you a whole bunch of words there in the little theorem box. But that's basically what it is. Factors of the constant term divided by the factors of the leading terms. Those are the only possible, that's the form of all possible rational zeros. So, like I say, that does not include the things like the square root of 5. That's not rational. That's an irrational number. Doesn't include any complex numbers. It just tells me what the nice numbers are. So, I'm just going to go ahead and jump down to checkpoint 2. So f of x is 4x to the 5th plus 12x to the 4th minus x minus 3. Okay? Everybody see that? So my possible rational roots, or zeros. I think in this book they call it zeros, are the factors of -3 divided by the factors of 4. All right, so the factors of -3 are positive and -1 and positive and -3, right? Because I could take positive 1 and -3, and I could take -1 and positive 3. Everybody understand that? The factors of 4 are positive, negative 1, positive and negative 2, and positive and negative 4. Because I could have a positive 1, positive 4, or I could have a negative 1, negative 4, right? So I do have to take into account all of the signs. So here is my list of possible rational roots. I can have a positive negative 1 over 1, positive and negative 1 over 2, positive and negative 1 over 4. I take this 1 and I put it under over all the possibilities for the factors of 4. Then I take the 3's. So I have 3 over 1, 3 over 2, and 3 over 4. Now, if you have a lot of factors, sometimes some of the factors overlap, and you don't have to write them in your list more than once. But in this case, we just get those 6 factors. So if you were going to use this with synthetic division, you would take these as the numbers that went inside. And the only things possible to divide evenly or to give me a 0 remainder would be one of these 6 numbers. So you are sometimes going to be using those fractions that you didn't like. Okay, Ethan? Okay. Everybody understand that? What this does is this tells us. Now, how are you going to use this in the real world? Because I know you have a graphing calculator. And what can you do with your graphing calculator to find a 0? Take not second graph. That's probably not your best option on this one since there are a lot of them are fractions. But take your equation, put it in y equals, and look for the places where it crosses the x-axis. And so, if it crosses at 1 or 3, you'll be able to see that. But the way this list is nice is that if you're looking at it and you see that the graph crosses somewhere between 0 and 1, then the 0 that we're talking about has to be this positive 1/2. It's not a 1/3. It's not a 1/4. It's not a 3/5. Okay? Everybody understand what I just said to you? And how to use this list with your graphing calculator to make the most efficient use of your time. Okay? All right, so that's how you use this possible rational root or possible rational 0 theorem when you're actually trying to find the zeros of a polynomial function. Now, section 2 here is actually finding the zeros of a polynomial. So let's go ahead and follow through with the process that we're talking about and actually find all the zeros. So let's look at checkpoint 3. So we've got f of x is equal to x to the third plus 8x squared plus 11x minus 20. So my possible rational roots or zeros, how about that? Will that work? Possible rational zeros are the factors of negative 20. So positive negative 1, 2, 4, 5, 10, and 20, right? Over the possible roots of the leading coefficient, which is just 1 in this case. Everybody see what I did? Take the factors, all the possible factors of the last term divided by all the possible factors of the first term when it's in descending order. And so these are my places where I can possibly be crossing the x-axis with this. So you can pull out your calculators. Go ahead and pull out your calculators. And type in y equals x to the third plus 8x squared plus 11x minus 20. Well, it's right up here. Push the over button on the arrow. Okay. All right, so what does it look like this graph crosses the x-axis to you? Maybe a -4 Well, -4 is in my list, so I'm going to take the -4, and I'm going to use my synthetic division. And double check and make sure it really is a 0. So bring down the 1, -4, +4 gives me -16. So I've got -5, gives me +20, so that is a 0. Okay, so -4 is 1, 0. -5 looks like another one. Now this is what I was talking about the other day. If you can see more than 1 on your calculator screen, you can go ahead and continue to do synthetic division. So you can just take that -5 and put it there. And so you'll only be working with the things that come before the remainder. But you can just do synthetic division again if you can see it on your calculator screen, because this is your check. This is the way you show me that you know for sure this is a 0. So bring down the 1, -5 gives me -1, +5, so that is a 0, right? So then I've got -4 and -5. What? No. You do it with what's left over. That's what I'm saying. Do successive divisions, because now what this says to you is that 1 times x minus 1 is equal to 0, so x is equal to 1. When you get it down to where there's just 2, that's linear. You can take any linear equation and solve it for x, right? So every time you do a synthetic division, you reduce the exponent by 1 because you're dividing by x. And so it just gets smaller and smaller. So if you can see the zeros on your calculator screen, then just go ahead and continue to do successive divisions until you get down to here. And then just set it equal to 0. Okay, so my zeros here are x equals -4, x equals -5, and x equals to 1. And that should have been what you saw on your calculator screen where they crossed. Okay? So that's how you use your graphing calculator with this synthetic division to prove to yourself that you have actually found the 0. And that is necessary. Because remember, with the graphing calculator, depending on what your window is, it may look like it crosses at -4, but it may be crossing at -3.999, right? Y'all following what I just got through saying to you? So be real careful with that, because you can get round-off error on your calculator, whereas it doesn't happen here. So give me an exact answer. Make sure it's right. Okay, any questions about how to find zeros of a polynomial like that where all the zeros are real numbers? Okay, so let's look at checkpoint 4. Because remember, not all zeros will look like that. So first of all, I want to look and see what are my possible rational zeros. So possible rational zeros, we've got positive -1, positive and -2 divided by positive -1, right? Factors of 2, factors of 1. So it's just going to be one of those 4, right? So you can just choose one and guess blindly. That's what we used to do back in the day. We didn't have a graphing calculator, so we just kind of chose one and tried it. When there's only 4, it's not a big deal. If you got your graphing calculator out, you can stick that in there and you can guide me about which one we should try. My guess is it's positive or -1. Is one of them anyway. That's just a guess. Plus, I always start with positive -1 because it's just the easy one to do. You can do that real quick if you're testing it, right? You don't have to be able to multiply anything, right? So that's what I would start out with, is positive or the -1. Does anybody get it on their calculator screen? It kind of looks funny, so it's hard to tell. Well, let's just go ahead and test it then. Let's just try maybe -1. 1, 1, -5, -2. Bring down the 1. We got -1. That gives me 0. 0 is -5. Nope, that ain't it. That doesn't give me a 0 remainder. So I know that -1 doesn't work, so I can try +1. 1, 1, 2, 2 is negative 3. Negative 3, that don't work. So we'll try 2. Bless you. Ah, there it is. So it's positive 2 is my first solution. Everybody see it? So I need to pick it up a little bit so you can see it. Okay. Now, since it's very hard to see anything else on there, what I'm probably going to do at this point is I'm going to do A, B, and C. Remember, if we've got it down to 3, I can do quadratic formula with it to find the rest of them. The only time you continue to try to do successive synthetic division is if you can actually see the places where it's crossing on the x-axis and you can kind of get a good guess at what it is. Okay? So one solution here, one 0 is 2, and I've got to find the other 2. Now I'll find those with the synthetic division. So negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 over 2 times 1. I've got x is equal to negative 3 plus or minus the square root of, this is 9 minus 4, which is 5, over 2. So my solutions are positive 2, negative 3 plus the square root of 5 over 2, and negative 3 minus the square root of 5 over 2. So if you get something weird looking with your graph and you can't really tell where the thing's crossing, just go back to the rational roots, try those until you find one that works, and then if you're down to the quadratic formula, then you can just plug it in the quadratic formula and find the other 2. If there are 4 roots, then you've got to do synthetic division twice, right, before you get down to where you can use the quadratic formula, just to the 4th power. Everybody understand what I just said? Any questions? All right. Okay. Now, objective 3 says solving polynomial equations. What are solutions? Same thing as zeros. Very good. Okay? So is this process going to be any different? No. You do have to kind of be careful. Pay attention to what kind of roots you're getting. Okay, so there's my equation. How many roots is it going to have? 4, right? It's going to have 4. Now, remember, sometimes we have things that have a multiplicity on the roots, right? Some roots happen more than once. How can you tell if it's an even number of times that it actually happens by your graph? The graph comes down and touches and then bounces off, right? Got to have at least a multiplicity of 2 if it bounces off. So, you're looking for things like that. You're looking for little hints to tell you what to do. Also, the other thing that and this is in the properties of roots at the top of page 332. It does talk about counting the multiplicity separately so that you get actually 4 different roots. And then it tells you that if a plus bi is a root, then its conjugate is also a root. They only exist in conjugate pairs. So if you have 2 plus 5i as one root, then you've also got 2 minus 5i as the other root. They only exist in conjugate pairs. Everybody hear what I just said? That's a real important idea. Okay? All right. So we've got this problem here. We're going to try to solve this. It's set equal to 0, so I'm finding solutions as opposed to finding zeros. But it works the exact same way. What are my possible rational roots? We're going to call them roots this time because we're solving, as opposed to a 0. I don't care what you call them. positive and negative 1, positive and negative 13 over positive negative 1. Everybody get that? All right? Everybody understand possible rational root theorem? Okay. So, I need to know, of those four things, what's going to divide evenly with a zero remainder into this polynomial. Anybody got it on your calculator screen? Anybody got any ideas for me? I think I'm going to try 1. I want to work with 1 instead of 13. So I'm just going to try 1. Since y'all hadn't told me what to try, I'm going to try 1. Bring down the 1, we get 1, we get 7. 7, you add that together, you get 29. 29 gives me negative 1. Darn it. That one doesn't work. I sure was wanting positive 1 to work. So well, let's try negative 1. I really wasn't wanting to play with that 13. Alright, so there's 1, so I get negative 1, and there's 5. So I get negative 5, what does that give me, 17? Negative 17, nope, that isn't going to work. That's going to be too big. So I guess I'm reduced to playing with the 13s. Has anybody looked at it yet to tell me if it's a negative 13 or a positive 13? You do have to get your window bigger to look at the positive and negative 13 on the x-axis, right? Because your standard window only goes from negative 10 to positive 10. So, it didn't work? I don't think this is going to work. Okay. So, it doesn't look like it actually crosses the x-axis anywhere. Okay, so what does that mean about my solutions then? They're all four imaginary. Okay? So I don't think I remember there being a problem like this. Yep. That one does work? I was going to say, they don't give you any problems in this book at this level where you don't get at least one rational root. So did I mess up then when I wrote the problem down? Oh. And you wrote it down wrong too? You weren't paying attention? Okay. Alright, so we'll try that one again then. Yay. Alright, so one works. And then I want you to remember that this turns into x to the third minus 5x squared plus 17x minus 13, right? A lot of y'all did that very well on the quiz just a minute ago. You do know how to go from what's here to here. The reason that that's kind of important is because this tells me that this is the factored form of that, right? Now I can look here and maybe try to do something with this one. I don't think it'll factor by grouping though. Can't put it in the quadratic form yet, so I'm hoping that -1 or another +1 works again. Does it at +1 actually bounce off, or does it cross through at +1? Oh, so let's try +1 again. Because if it bounces off, that means that if the graph bounces off there, remember it means I've used it at least twice. Has to cross through for it to be just 1. Yay. Okay. So now I've got 1 is a 0, but it's just, I just have to write it down once, right, even though its multiplicity is 2. And I have 2 more zeros, and now I have it down to the quadratic formula. So now I've got A, B, and C, and I can put it into the quadratic formula because I had 4 of them and not 3 of them. I don't have an A, B, C, and D. There actually is a formula for that, but it's got several steps, and then we don't ever use it because it takes way too long to work with it. And the bell's going to ring on us in just a second. So if you'll look here, you'll notice that this is going to be a complex number. Everybody see it? And so you're going to have 2 complex numbers that's going to be part of the solution. Okay, the rest of the stuff that's here, not too bad. I'm going to go ahead and give you the entire assignment, and then you can attempt it. Look at the set. That's on page 335, and you need to do 4 through 64 multiples of 4.